Charles Aznavour, probably, right, isn't it? Sounds like him. Dead now. So I'm not sure what drives people to do this. I guess it is fun to get sandblasted and stripped of your clothes, perhaps as well. I'm not sure, but it's obviously it's kind of a twist on our F-150 on San Francisco apron, I guess. So I'm sure you've seen many of these bizarre movies. Anyway, so that's fluid mechanics at some level. Yeah, maybe it's depleted by the by being washed into the sea. So real fluid mechanics now. So one of my colleagues, one of your former professors before your time, left here to be chief scientific officer, I think, for Ingrain. It's kind of a startup that got bought out by Halliburton. But their idea was quite clever, I thought. So you'd get the drill trips that come up, the cuttings that come up a well bore in shale wells, or it could be any wells for that matter. And you'd like to know what the permeability is of those chips, but they're too small to do experiments on. So what you could do is you could on-site micro CT, X-ray CT them to get the shape of the pore space. If you see there's some round spheres here. So this is just a bead pack of spheres with spaces between them that water's flowing in. And then once you've X-ray CT'd them to get the architecture of the porosity and its topologies, you can run a model to be able to flow fluids in it that stick with zero velocity boundary conditions at the edge of the pore, just like we talked last time in a pipe, and come up with the net outflow on the downstream side for a pressure gradient that you apply between upstream and downstream faces. So these colors are pressures, going from high pressure to low pressure, red to blue, and for multiple liquids, right, from gas and water flowing at the same time, which is what you'd have in a shale gas well, for instance. So very kind of an intriguing idea. They were they're bought by Halliburton, I guess. So I think the idea of the startup was to sell it to someone, and I'm sure they made a bit of money. And so these are much more sophisticated things that we'll try in this class. But fluid mechanics, we'll talk about how to get the differential equations of flow, which are, you'll see shown in some of the moment, how we solve these numerical problems. But this is just a jet of water being sprayed into a growing bath of water, solving a bunch of equations that allow that to happen. No different from the equations that we're talking about in this class, but maybe a bit more sophisticated. Often it talks about particles, many particles. Okay, I guess we've finished with that one. Some of them more interesting. I guess this one. Yeah, this is same idea. So particles, you could imagine this jet of water being made up of tiny little particles, all of which are satisfying F equals ma. We talked about that water just satisfies F equals ma. And this next one is much longer, I guess, so I can talk. Yeah, fine. And the idea is that NVIDIA, I guess, high computer power needed. NVIDIA, the AI chips that are often in the news, and the company that's burning on the NASDAQ, I guess, right, isn't it? The tech stock market. And this is exactly the same thing. You represent the body of water by a whole number of particles and just allow them to slosh around according to some laws. You do some things with a jet to be able to push it in. You can float blocks in it. I think in a minute. And then you render it somehow. So these aren't just straight numerical model results out of it. And so these are used in, is it CGI? It's computer-generated graphics, or whatever the acronym is for movies. You run the model, you get the curtains blowing in the breeze, and then you drape some image over it to have the curtains rippling in the air as the air blows over it. And this is the idea that you can devise a mesh of all these tiny little, they'd be cubes, I guess, prisms or cubes, that you can have water flowing through in on one side, out on the other side, so you can account for exactly where it's going, and you can solve the appropriate equations of motion of fluid to be able to make these kind of cool graphics. And I remember a few years ago, the Academy Awards have awards for computer graphics, and so these are all done with very high power numerical models to represent situations, and then to drape images on top of them so they look realistic. Quite so. And so they all rely on the idea that you could divide your world up into a whole series of little boxes and look at water flowing into it, look at water flowing out of it. What doesn't come out the other side accumulates. Sounds familiar? It's kind of conservation equations. So conserving mass, volume in equals volume out, and what doesn't come out accumulates. And also solving momentum balance, that F equals ma, what we talked about in week 7 last week. And the final one, I guess I'm not sure if this is stalling out. I guess it's not stalling out because it's running. But this is, something else. And so you drape all kinds of graphics on it and have water sloshing over a lighthouse. Pretty realistic, really. I think it's not something we'll attempt in this class, but the principles of this are really nothing different from what we've talked about. So perhaps that gives motivation to be able to do these things. Really quite amazing when you think about it. So real time, I guess they're making the case that this simulation is in real time. So the modeling, the computer that's running right now is giving the output at the rate at which you see it on the screen. And so really quite powerful ideas. And I can't remember what the other one was. Oh yeah, and by that standard, somewhat a little more mundane, but this is groundwater hydrology modeling, which we will talk about. Plan view of a dam and a grid with rivers coming into the dam, and somewhere there will be a side view of this. I'm not sure exactly, right there, I guess, and I'll stop it. So the idea that you have a dam, you have the strata under the dam. I guess I can hear the background. One of the things is running. I'll talk over it. And you can divide the soil or the rock up into these boxes and do exactly the same thing. I guess he's talking in this case. Yeah, stop it. So you can divide the rock into boxes, inflow one side, outflow the other side. What doesn't balance accumulates, and you can write some very simple equations for that. These are much simpler than the ones we looked at for the lighthouse and the other ones, but the same idea. It relies, in this case, on conservation of mass, with an extra term, Darcy's law, added to look at the head losses in the system. And perhaps we'll talk about that if we get to it today. Okay, so that's the eye candy stuff for now. Any questions so those are things we'll talk about today. Questions before we get going? The test stuff is online. Review is online. It says exactly what it will be. Free jets, conservation of linear momentum and rotational momentum. I will say, when I'm asked individual questions about it, I don't usually respond, rather do it for everybody. I've got a question about whether it's a linear jet or a parabolic jet. I think we didn't. All the questions are stuff we've done in class, examples, and we didn't do a parabolic jet in class, as I recall. So that's as much as perhaps we need to say. So, to me, again, look at the review, look at questions in the past. They are retreads of previous questions with numbers change. So at least it gives you somewhere a bite-sized place to start, because we have covered a pretty broad swath of stuff in this class. I realize it might be like drinking out of a fire hose, but hopefully a useful fire hose. Yeah. So, any other questions before we get going? Same format in class. A bunch of people will be out for SPE conference in Houston. I guess I have some names from John Yilin Wang of who's out, and so hopefully you can all make it. Yeah. Okay. yeah, never pleasant to talk about such things in class particularly. All right, 8.2. Well, recap, might just go back to what we talked about last time and run through it. I mean, it's quite, it was lots of equations, but I think we cut it down to something a bit simpler. The idea was that we could define two equations by looking at conservation use of energy using Reynolds transport theorem, and we could do it by either substituting mass times energy, total energy, and the total energy was something that we'd seen before: elevation head, velocity head, pressure head, but internal energy per unit mass. That represents maybe water flashing to steam, releasing the energy that it has in thermodynamics. And this term is lumped with pressure. It's gone off again. Is it going to come back on? It does. It's thinking about it. I'm pretty sure I'm not doing anything. I don't know if it's a bad cable. And so enthalpy gets put in here, these two together. Joules per kilogram, so energy per unit mass. Strange units for this because this is meters squared per second squared, but you can do a conversion by just multiplying by kilograms over kilograms 1 to be able to get this is actually in joules per kilogram if you manipulate it. Substitute this into Reynolds transport theorem and you get an equation that looks like Bernoulli, but with net heat in and net mechanical work in added to it. And of course, actually it's not work, it's power. It's rate of doing work. Didn't even have any whiskey last night and I can't speak. And so these are power, units of watts, joules per second, Newton meters per second. And the only case we'll look at is a single 1D case of a stream tube where you can look at the amount of work you get out of the system if you have a certain amount of enthalpy going in and coming out, velocities going in and coming out, and elevation changes. We did one example with a compressor or a turbine to see what that net energy production was. We won't use that so much. We'll use the other one much more, which is Bernoulli's equation here, which is also written between upstream and downstream, with the pump head added as the energy into it, similar to this, and the head losses in the system. Has to be written from upstream to downstream because of the sign conventions. Pump, if this term is positive, it's putting energy into the system to pump uphill. If it turns out that this is negative, it's a turbine and it's removing energy from the system, power from the system. Head losses are always positive. Friction losses are always act against the motion and they're always positive. The other expression that's important for this is that the pump head can be defined as power divided by a volumetric flow rate times unit weight. And this lower term is also the same as volumetric flow rate times rho is mass flow rate, and g is gravitational acceleration. And so we can always define that. So we just have to be careful to write it in the right sense from upstream to downstream always. And the graphical representation of this is that the pump head is an extra part of the stack of elevation head, pressure head, velocity head, pump head. The two sides of this equation have to equal each other, and so this is a horizontal line, and the head loss is just what makes it up to here. Pressures, it could be that, well, we'll talk about today. What else do I want to say? Nothing. We did one example for a dam, just to show that we always have to work against head losses. In this, if we're allowing the reservoir to flow downhill, then we get the pump head comes out as negative, so it's negative as a turbine, so it's producing that amount of power. And we can always get the amount of power by using this. So the other way to write this expression, I guess have a little bit of space down the bottom, is that we could write this by, if we assume, for instance, that this is 0. If we assume that this is 0, then we could write this expression as delta Z, which is Z1 minus Z2, is equal to HP, which is equal to W dot over Q unit weight, which is that the amount of power you could get out of a dam is just equal to the head drop times the volumetric flow rate times the unit weight. And so if you have a dam which looks like this, so you're putting water through the dam through a tube, big reservoir assumption, velocity 0, etc., which is how we got this. Then the maximum amount of power you can get out of a dam is going to be the height, the relative head across the system from the water level to the turbines, times the flow rate, times the unit weight of the water. So this is just rho g, right? So you can always convert that into something. So you can always find the output of a dam. So, for instance, if you're thinking of a steady state system in a atmospherically steady state, in a year you'd have such amount of rainfall over the catchment area of the dam. That would be the water that, if after removing evaporation and transpiration, would end up in the reservoir. So that would be the maximum amount that would be available to go through the dam in a year. And so you could calculate what you'd expect the power rating of the dam to be as so many megawatts, right? That would be the rating. So that's an easy way to, a practical way, I guess, to think of the things that we're talking about. Okay? All right. Didn't do that question. Yep. Hit me.
Just to be sure, we're referring to power as capital Z in this case, correct? Or
Power is, so yeah, so in terms of our terminology, I have used mass flow rate, and I guess we've also, expletive deleted. Thank you. We've used this, these are equivalent. This is mass flow rate. We've used velocity, relative velocity, static velocity, relative velocity, and velocity of control surfaces. We used volume, and we've used, this is power, which is Newton meters per second, which is equal to joules per second, which is equal to watts. So thermal power plant, a big thermal power plant is a gigawatts. That's the rate that it produces power every second of the day, every day of the year. And the total energy that would be reported, energy would be, we don't talk about energy so much. I guess we did in that we called it E. This would be joules, or kilojoules. Okay. I try and be consistent with these. Yeah. So this is mass flow rate. Sometimes we've often used uppercase M. This is power. This has to be the same units of thermal power, etc. Okay. And this is the equation that we just mentioned, where I called it, yeah, uppercase M. So I guess I use them interchangeably. Okay. All right. So I was going to do a couple examples today, and then talk about differential analysis. So this is what I planned. So rather than scribble over what I have, I thought I might try and pull these out. See if I can do it. Maybe. What a hero. Cold season. Sounds like it. All right. So getting there. Hopefully getting out the other side of it. All right. So this is an example. So we won't go through putting numbers into it, but we can do everything else. So you have a pump. It's transferring water from a large reservoir to another large reservoir. It's using a pump. The elevation gain is 100 feet. Presumably it's flowing in this direction, because if you didn't, you wouldn't need a pump otherwise, right? It'd flow from high to low otherwise. And so pump transfers water between two reservoirs. The difference in elevation is 100 feet. The frictional head loss is equal to a constant times V squared. So in this case, head loss is equal to a constant times the average flow rate squared over 2G. We know this is a unit of length. V squared over 2G is length. K must be a constant, and it is. We work in terms of the average velocity within the pipe, which we're interested in. KL is the loss coefficient, yes, considered constant. The relation between the total head rise across the pump and flow rate Q through the pump is given in this figure here. And I guess we know that KL is equal to 20. So no units, since this is length, so it can't be units. The pump head is given by this equation here. It says that if you only want to pump at a very low flow rate, you can pump very high. But if you want to pump at a much higher rate, you can only pump a small elevation. It's a true behavior of pumps, and it kind of intuitively makes sense. So the pump head from this is just the fitting of this equation, which is that the pump head is that the pump head is equal to, you're not given this, but you can see why it would come from this, times 100. So when the flow rate is 0, the pump head is equal to 200. So the flow rate is 0, 2 times 100 is 200. And it would be 200 feet, I guess. When the flow rate is equal to 2 cubic feet cubed per second, this would be cubed, not squared, then the pump head is what? So 2 minus 2 is 0, times 100 is 0. So that's just the equation of this line. It's a straight line, so it's a linear expression. So what do we know about this system? We can write out this equation. I guess I perhaps don't need to write it again. Big tank assumption. Big tank assumption at the top. Here, right? No velocity here. No velocity here. We have atmospheric pressure on the top of the tank. So I guess I didn't say, we're going to write Bernoulli, a stream tube that goes up through here and ends up at this point here. Pressure at point 1 is atmospheric. Pressure at point 2 is atmospheric. we have a pipe diameter of 4 inches. What is the flow rate through the system? So we want to calculate. V average, and Q is equal to V average times cross-sectional area, right? This is what we want. This is Q. So we could assemble this set of equations if we want to. We're left with what? We're left with a value of Z1. We're left with a value of Z2. We're going to want to solve for, we have HP, and we need to calculate HL. And so we want to be able to solve for Q. But we only have Q as a function of this expression here. So I guess we're going to want to isolate this term here. And so we could rearrange this equation to write HP is equal to Z2 minus Z1 by moving this term onto the right-hand side, plus HL. And we need to be able to write these terms in terms of Q. So we know what this is. Z2 minus Z1 is just going to be equal to 100 feet. So we know that. And so we need to figure out how to deal with these two. So HL is equal to the head loss term multiplied by V squared over 2G. I guess we're going to want to write this in terms of volumetric flow rate. So we also know that Q is equal to V times cross-sectional area. Area would equal to be pi d squared upon 4. I don't want to work with the English units, but this is what they would be. And so if we can rearrange this to be in terms of velocity, then average velocity is equal to volumetric flow rate over A. So HL would be equal to a loss coefficient, which we know is 20, 1 over 2G times Q squared over A squared, I think. And we know that the pump head is equal to 2 minus Q times 100. So everything we've done in this class really has been in consistent units, but clearly this isn't, right? This is a length is equal to a volumetric flow rate. And it matters, although they didn't say it, that this volumetric flow rate has to be in the right units. So Q in feet cubed per second gives you these coefficients, and this gives you a head in feet. They don't say that, but that has to be the deal, right? This is not dimensionally coefficient. Length is equal to length cubed over time. So you need to be aware of that. And so now, I guess, we have an equation which we know this, and the only terms we don't know are Q and Q in this one equation. One equation, one unknown. We know 100, we know 2, we know that this is 20, and we know G, and we know the area because we know the diameter, and you know everything. And so you just need to solve for that. I'm not going to solve it, but it's going to end up being a quadratic equation. So I'll just zoom down to the solution so you can see that. You end up with this, right? If you work through it. The solution's there. So setting up the problem is a difficult part. Getting the solution, I think, is perhaps less. But we have a Q squared term in the V squared over 2G term. So that's this. This is the pump head term, 2 minus q times 100, and this ends up with that. That's it. So just need to you need to manipulate it to get an equation that you can solve for the value of q, but q is a bit complicated because it's a quadratic equation. Yeah. Too difficult for an exam. So if you want to hear that, but that's how we'd solve that question. Right? Another one. Yes, I heard an agreement. All right. All right. So, problem statement. Flowing gasoline through 2 pipes. So gasoline has a density of 0.68 times that of water. So the unit weight of the gasoline is equal to the unit weight of water times 0.68. Or density is equal to 680 kilograms per meter cubed. I'm not sure which we need. It goes through a pump at a flow rate of this. So Q is equal to 0.12 meters cubed per second. Blah, blah, blah. Head loss is equal to 0.3 average velocity through pipe 1. So I guess that's the wrinkle here. V squared over 2. And pipe 1 has a different diameter to that for pipe 2. So I guess we know that the area of pipe 2 is equal to pi d2 squared upon 4. And the area of pipe 1 is equal to pi d1 squared upon 4. And we know that velocity 1 times area 1 equals velocity 2 times area 2. So we can always write one pipe in terms of the other. So I guess we're probably going to need velocity 1 being equal to area 2 over area 1 times V2, because we have this term here, I'm guessing. And then we need to write Bernoulli's equation in terms of these. Okay, so what do we know? We have what is the head loss between sections 2, and that's what this magnitude here is. You asked what's the difference in pressure between 1 and 2. So that means we want to know what P1 minus P2 is. So we can rewrite this equation as P1 minus P2 over unit weight of gasoline, just by moving this term over here. And we can write it in terms of everything else. And so it's going to be equal to V2 squared minus V1 squared over 2G. It's going to be Z2 minus Z1. And it's going to be minus HP. And it's going to be plus head loss. So what do we know about this? We know that Q is equal to 0.12 meters cubed a second. So we know that V1 is equal to Q over A1, which is equal to, well, 0.12 meters cubed a second over A. Not calculate A1, but we have the diameter. So we know what we know what V1 and V2 are, because V2 is just equal to Q over A2, whatever that is. So we know this. We know this. We know that this is equal to 3 meters. We know that HP is equal to power divided by Q rho G, or I guess which we need. And so we know that those terms are 20 times 10 to the 3 Newton meters per second. That's 20 kilowatts. Volumetric flow rate is 0.12 meters cubed per second. Density is 680 kilograms per meter cubed. And gravity is 9.81. And so, a Newton is the force needed to give a kilogram an acceleration of 1 meter per second squared. So that turns out this term should be ultimately in meters. I won't calculate that. And I guess we have the head loss, which is equal to 20 times V1 squared over 2G, and we know what V1 is. So, a bit messy, but you get the idea. So, we can write the equation out. I hate writing. I don't know why I wrote it in this terms. This is just HP, right? I like writing Bernoulli in length, just commits to memory very easily. And so we have everything we need to calculate this. You can rewrite Bernoulli in terms of this. Hopefully you've got our signs right. Upstream to downstream, always positive, positive or negative. In this case, it will be, the value of this will be positive because it's pumped. But when it goes in, it'll be this sign, is because we swapped it from one side to the other. But our sign convention is if it's a pump, then it's positive. Pump is positive. Turbine is negative. So if, in other words, we're allowing it to flow from upstream to downstream, then probably for this equation, if we had it in the right units, it would give a negative value for HP in terms of coming out of the equation. And everything else we have. We have velocity here. We have velocity here. We know that it's a steady state system, so the volumetric flow rate has to be the same as it goes through, so we can write continuity. So we can get the velocities 1 and velocities 2. We are told what the elevation difference is as we go up it. We can calculate what the pump head is from the power of the pump, and we can calculate what the loss is because we absolutely know what the velocity is of the flow that's going through it, and it's written importantly in terms of the velocity in pipe 1. This is what we would have called before the average velocity with an overbar. not -2, but an average velocity. Perhaps I'll leave that out. So, okay. So, kind of a marathon calculation, and the solution's there if you want to look at it. It ends up being not so incredibly difficult. And then I guess what you want to do is when you solve this, you just multiply P1 minus P2 is equal to P1 minus P, obviously. And you have unit weight, which is just, unit weight is just the density of the gasoline times 9.81. Okay? So. All right? That's what we do today. So, straightforward. Just a matter of setting the problem up correctly and being able to work through it. Lots of manipulations. Easy if you've seen the answer before, not so easy if you're seeing it for the first time, but anyway. Okay? All right, I'm never quite sure whether you're with me or dead. So, all right, let's move on. Don't want to do these equations. Yeah, I'll do it differently. Right. We okay? That's yes? Or a question, yeah. Good. All right. So we started this session off by looking at these fancy models. And so one of the things to look at is differential analysis. Shouldn't call it that. It's too off-putting, perhaps. But many of you will deal with equations of motions of fluids and porous media, like the In-Grain movie. And actually, we've already addressed this. We said that if you have, we already wrote this expression down. If we have our differential cube that we've had in the past, what we can use is conservation. It's not very cubic. We did this already once, but let's do it again. If we have fluid flowing across this system, and we have a coordinate system, x, y, z, and we have V1 and V2. If we have conservation of mass, we have something like rho V dot plus V rho dot, rate of change of density, plus sum of velocity, area, density equals 0. And so if we assume that the volume of this doesn't change, this little differential cube, and that we write the dimensions of it in terms of the dimensions in each of these coordinate directions, if we resolve in the x direction, then we get something like volume multiplied by rate of change of density plus V2 minus V1. Right? This term here, it's coming out of our system, so it's positive. It's going into our system, so it's negative, times the area of this face. Not doing it for me? Okay. This marker, this one. The area of this face is equal to what? dy times dz. And we can multiply that by dx over dx equals 0. And so we could rewrite this as the volume of this control volume, a rate of change of density with time, just writing this out in full, plus change in velocity, which is these terms here, lowercase v, divided by dx, times dy dz dx equals 0. So likewise, this term here is volume, right? And so what we could write this out as is, well, we could divide both sides through by volume. In which case we'd have rate of change of density with time plus dvx dx, the rate of change of velocity in the x direction, equals 0. It turns out that if we did it in all three directions, we'd have, well, let's not do it in all three directions. And so we said last time, or some other time, wasn't last time, that we could do an experiment to be able to flow water down a cylinder filled with sand, and we could drive it over a length dx, and the velocity that would come out of the system would be given by Darcy's law. A coefficient times, let me write it in terms of permeability, change in pressure over viscosity dx. This is pressure, this is density. So this is Darcy's law. Actually, there's a minus sign in here because if you look at the pressure gradient and x direction, the flow is in the x direction for a negative pressure gradient, hence this term here. And if you take that term and substitute it into this expression here, you get something which is d dx pressure I guess I'll write this in just to not perhaps it does confuse you. So the net result is that this is density, this is pressure. These are the groundwater flow equations. And we solve these relatively straightforwardly in that last example that we talked about. And I guess the only important thing is that we can, if it's steady state, then this gives an expression which is, if it's steady state, this term isn't changing. So this is just k over mu d2p dx squared equals 0. And these are the equations of groundwater motion. If you're a groundwater hydrologist, you might have seen there's the term which is the storage. And actually what we do with the storage term is that we would multiply this by pressure over pressure. And as a result of this, so the rate of change of is, if you multiply this by So the term 1 over rho 0 is compressibility. First week of classes, we talked about the compressibility of gases. So the rate of change of density if you apply a pressure in a bicycle pump is given by a coefficient, which is called the compressibility, which is in units of 1 over Newton per meter squared, pressure, pascals. And so we can use this term to be able to substitute in d rho dr would be equal to, sorry, d rho dt, btp, would be equal to density multiplied by beta. So the full term actually becomes, if I remove this part here, it is still steady state. Actually, it's not going to be steady state. Is if I put this term in here, this would be dp dt, pressure times time, or pressure with time multiplied by density times compressibility. And I guess I have left out one term here, right? Notice what it is. No density, no density, no density, no density, and no density. So this density would cancel out in all of these. But this is the equations of groundwater flow. So if you're a petroleum engineer, then why don't I make some more space? So if you're a petroleum engineer, or a geothermal engineer, then you'd write something like compressibility times rate of change of pressure with time. There's a minus sign in here, which I neglected. So this now would be a plus K permeability, viscosity of the fluid, d2p dx squared. And this would be equals. And if you're a groundwater hydrologist, so you'll see the, I don't know if you've seen these equations in your activities so far. It would look something like specific storage, rate of change of head as a function of time instead of pressure is equal to hydraulic conductivity d2 head dx squared. And head is just equal to pressure over unit weight plus elevation plus v squared over 2g, but we don't use that. Take this as 0 because it's slow in comparison to everything else. So in your careers, mining engineers will use it, groundwater flow into mines. Energy engineers, geothermal energy, typically use pressures because it's multi-phase fluids. And so this is the basic form of the expression. And to kind of circle all the way back, all it's saying is that the basic conservation of mass equation steady state is just dvx dx. If we do it in all three directions, take this on trust, plus rate of change in the z direction with z is equal to 0. And so this is the general conservation equation for mass if we ignore the terms, and it's purely come from our conservation, the sum rho VA equals 0. It's just that we've assumed two things. We've assumed both of these transient terms are 0 in this case. We assumed that the change in density was not 0 in this particular case, but if it's equals 0, that's the case. And all we've done is calculate what this is for fluids going in and out of this cubic volume, dx, dy, dz. And so that's the basic relationship which is used for Darcy's law. To substitute Darcy's law into this, and so interestingly enough, the equations of motion for groundwater flow come from only conservation of mass, where this term for Darcy's law, where it's represented in terms of Bernoulli as this. I know I'm running a bit late, but let me finish this thought. Remember, from upstream to downstream, Z1, Z2, P1 over gamma, not unit weight. And an equal amount here everyone's getting ready to go. And this is HL. So this is exactly what's driving it. We've talked about Bernoulli being maybe in a pipe with V2 and V1. If the upstream and downstream areas are the same, V1 and V2 squared have to be the same height. But the elevation, if it's a horizontal pipe, have to be the same. But the pressure loss between upstream and downstream is taking care of this HL term. This HL term is basically Darcy's law. So if you filled this pipe full of sand and pushed water down here, you expend some pressure in going from upstream to downstream. This head loss is that pressure loss. We just draw it denoted in a slightly different way and then substitute it into these equations. These equations aren't limited to flow just along a stream tube. They flow in all three directions, and you can develop pretty simple models that allow you to solve this equation. Very simple models. I've run over by 2 minutes. Okay, let's stop there. Thank you.